Hello! In this video, we are going to prove the following theorem. The limit as x approaches 0 of sine of x over x is equal to 1. Now, really, what we're considering here is the function f over the domain of non-zero real numbers. And it's defined by f of x equals sine x over x. So really, we want to show that the limit of this function as x approaches 0 is equal to 1. Right? That's really what we're doing here. But first, let's remind ourselves of the definitions we've been using. Our definition of the exponential function is as follows. For each complex number z, e to the z is the limit of the sequence 1 plus z over n to the power of n. And using this definition of the exponential function, we defined sine and cosine as follows. For each complex number z, we define cosine of z to be e to the iz plus e to the negative iz over 2, and we define sine of z to be e to the iz minus e to the negative iz over 2i. We also defined another function called the arctangent function, and we defined it as follows. Let x be any real number and consider the following sequence. Then we have shown that the sequence 2 to the n xn converges. And we defined the value that this sequence converges to be the arctangent of x. So all four of these are definitions. Now, from this definition of arctangent, we've proven a lot of properties. For example, one of the properties we proved was the following. We've proven that arctangent of x is less than x for all x greater than 0. We've also proven the absolute value of arctangent of x is equal to arctangent of absolute value of x for all real numbers x. We have also proven that the arctangent function is bounded, and we defined the least upper bound of the arctangent function to be pi over 2. In other words, we defined pi to be 2 times the least upper bound of the arctangent function. And with that definition of pi, we proved that the arctangent function is a function from the real numbers to the open interval negative pi over 2, comma pi over 2. In fact, we proved that the arctangent function maps onto the open interval negative pi over 2 to pi over 2. We have also proven that the arctangent function is a strictly increasing function. And that told us that the arctangent function is 1 to 1. And because the arctangent function is both 1 to 1 and onto, that told us that the arctangent function has an inverse. And we defined tangent to be the inverse of the arctangent function. And since tangent is the inverse, these two guys are going to get swapped. So tangent is a function from the open interval negative pi over 2, comma pi over 2 to the real numbers. Now, let's talk about some of the properties of cosine and sine that we have proven. First of all, we have proven that the cosine of any real number is a real number, and the sine of any real number is a real number. We have also proven the absolute value of sine x is less than absolute value of x for all non-zero real numbers x. We've also proven the cosine of x is greater than 0 for all x in the open interval negative pi over 2, comma pi over 2, right? Same pi that we defined via the arctangent function. We also have some other results regarding sine and cosine and pi. We have these results. And also, we've proven that sine and cosine are both continuous functions. In this proof, we're going to be interested in using the fact that cosine is continuous. Now, remember, our definition of tangent was that it was the inverse of the arctangent function. But at this point, we have proven that sine of x over cosine of x is equal to the tangent of x for all x in the open interval negative pi over 2, comma pi over 2. Another thing I should mention is that the arctangent of 0 is 0, right? This just comes from the fact that if x is equal to 0, then 2 to the n xn is a constant sequence of zeros, right? So we have that as well. So this is what we're working with. So now, let's get into proving this theorem. right? I'm going to circle the facts that we're going to be using in our proof. We're going to be using these facts in our proof. So now let's move back up to the top. Okay, so now let's get into proving this theorem. Now, before we prove this limit, we are first going to prove a preliminary result. And to start out, let's give ourselves an arbitrary real number x, which is non-zero and belongs to the open interval negative pi over 2 comma pi over 2. The claim is that cosine of x is less than sine x over x, which is less than 1. And so we're going to prove this. Now, since x is not equal to 0, we have, by this result, that absolute value of sine x is less than absolute value of x. Also, we know that x belongs to the domain of the tangent function. So, we can make sense out of the tangent of x. And we're going to let a be equal to the tangent of x. And since tangent is the inverse of the arctangent function, we know that x is equal to the arctangent of a. Now, since x is not equal to 0, this means we must have that a is not equal to 0. Because if instead a was equal to 0, well, we know that the arctangent of 0 is 0. So we would have arctangent of a is equal to 0, but that implies x is equal to 0, which is false. So yeah, we must have a is not equal to 0. And since a is not equal to 0, we have that the absolute value of a is greater than 0. But now we have the following observation. Since x is equal to the arctangent of a, the absolute value of x is equal to the absolute value of arctangent of a. And according to this property, the absolute value of arctangent of a is equal to arctangent of absolute value of a. And then, applying this fact, since absolute value of a is greater than 0, we have that arctangent of absolute value of a is less than absolute value of a. But a is equal to the tangent of x, so absolute value of a is equal to absolute value of tangent of x. So what we have shown here is absolute value of x is less than absolute value of tangent of x. And so putting this all together, we have absolute value of sine x is less than absolute value of x, which is less than absolute value of tangent of x. But now, the claim is we can modify this inequality so that we can get this inequality. And to see how we can do that, well, first of all, we're going to divide all three sides by absolute value of sine x. But how do we know we can do that? What if absolute value of sine x is equal to 0? So first, the claim is that absolute value of sine x is non-zero. And to show why that's the case, well, there's two possibilities of what x could be. Either x belongs to the open interval negative pi over 2 comma 0, or x belongs to the open interval 0 comma pi over 2. In the first case, we're going to show that sine of x is less than 0. In the second case, we're going to show that sine of x is greater than 0. So no matter which case we have that absolute value of sine x is non-zero. And so that's essentially the idea. Let's start with the case that x belongs to negative pi over 2 comma 0. Well, in this case, we know that sine of x is equal to negative cosine of pi over 2 plus x. And since x is between negative pi over 2 and 0, we have that pi over 2 plus x is between 0 and pi over 2. So by this fact, the cosine of this value is greater than 0. And therefore its negative must be less than 0. So we have shown that sine x is less than 0. But now let's consider the other case. If x belongs to 0 comma pi over 2, then we know that sine x is equal to cosine of pi over 2 minus x. But since x is between 0 and pi over 2, it follows that pi over 2 minus x is also between 0 and pi over 2. So, by this fact, we know that the cosine of this value is greater than 0. So sine x is greater than 0. So what we see here is, no matter what x is, the absolute value of sine x is not equal to 0. In fact, absolute value of sine x is greater than 0. So we can take this inequality and divide all three sides by absolute value of sine x. So we get this. But then we know that absolute value of sine x over absolute value of sine x is just equal to 1. We can combine these two guys into a single absolute value, just like that. But then, what is this guy equal to? Well, let's actually just re-express this guy in a different way. First, let's combine these two guys into a single absolute value. But then, we know that tangent x is equal to sine x over cosine x. So we get this, but then the sine x's cancel out, and so we're just left with absolute value of 1 over cosine x. Now the claim is, we don't need these absolute values. To see why we don't need the absolute values here, well, if we consider the two cases of what x could be, if x is between negative pi over 2 and 0, then sine x is less than 0. But also x is less than 0, so we're doing a negative divided by a negative, which is positive. So we don't need the absolute values. On the other hand, if x is between 0 and pi over 2, well then sine x is positive, and x is positive. So we're doing a positive divided by a positive, which is positive. So we don't need the absolute values. So then why don't we need the absolute values here? Well, because we know that the cosine of anything between negative pi over 2 and pi over 2 is bigger than 0. So we're taking the absolute value of something bigger than 0, so we don't need the absolute values. So we have this. But then, we know that all these guys are bigger than 0. So if we take the reciprocal of each of them, that's just going to flip the sign of these inequalities. So we get this. But then, if we just flip this around, we have cosine x is less than sine x over x is less than 1. And so, we have shown, given any real number x in the open interval negative pi over 2 comma pi over 2 not equal to 0, we have that this is true. And so, we have proven our preliminary result. So now, we're going to prove this limit. Now, by definition of the limit of a function, this means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in the non-zero real numbers, if 0 is less than the absolute value of x minus 0 is less than delta, then the absolute value of sine x over x minus 1 is less than epsilon. Now, I'm aware that you could apply a squeeze theorem argument using this inequality to prove this theorem, but I'm just going to prove it directly from the definition of the limit of a function. So, to prove this limit, what we want to do is we want to prove this statement. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a delta greater than 0 such that this is true. Now, to figure out what we should choose delta to be, we're going to use the fact that cosine is continuous. Since cosine is continuous, this means cosine is continuous at every real number. So in particular, cosine is continuous at 0. And by definition of continuity, that means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in the real numbers, if absolute value of x minus 0 is less than delta, then absolute value of cosine x minus cosine 0 is less than epsilon. Now, cosine of 0 is just 1, so of course we can replace that with 1. Now notice, These two statements are slightly different. If you notice the delta statements, well, actually, it's because there's a subtle difference. This comes from the definition of continuity. This comes from the definition of the limit of a function, right? They're slightly different, but essentially that's what we have. But now, using the fact that cosine is continuous at 0, this means we are given that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number epsilon that we have in our proof. So taking epsilon to be the epsilon we have in our proof, we have that there exists a delta greater than 0, such that for all x in the real numbers, if absolute value of x minus 0 is less than delta, then absolute value of cosine x minus 1 is less than epsilon. In fact, instead of calling this value delta, I'm going to call it delta naught. Because remember, our whole goal is to find a delta greater than 0 such that this is true. Now the claim is, if we take delta to be the minimum of pi over 2 in delta naught, then this statement will be true. So with this choice of delta, we proceed to prove this statement. And to prove this statement, let's give ourselves an arbitrary, non-zero real number x, such that 0 is less than the absolute value of x minus 0 is less than delta. From here, the whole goal is to show that absolute value of sine x over x minus 1 is less than epsilon. And to show this, it suffices to show that sine x over x minus 1 lies between negative epsilon and positive epsilon. So how do we show this? Well, why did we choose delta to be the smaller of pi over 2 and delta naught? Well, with this choice, we know that delta is less than or equal to pi over 2. And what can we do with that? Well, we know that 0 is less than absolute value of x minus 0 is less than delta is less than or equal to pi over 2. And absolute value of x minus 0 is equal to absolute value of x. So this tells us that absolute value of x is less than pi over 2. And that tells us that x is between negative pi over 2 and pi over 2. In other words, x belongs to the open interval negative pi over 2 comma pi over 2. And also, since absolute value of x is greater than 0, that tells us x is not equal to 0. So we have this. Because this is true, we can apply our preliminary result. So we have that this inequality holds. That's why we chose delta to be smaller than or equal to pi over 2. And if we subtract 1 on all three sides, what do we get? We get this. Now remember, the whole goal is to show sine x over x minus 1 lies between negative epsilon and positive epsilon. Well, we know that epsilon is greater than 0, so we have that sine x over x minus 1 is less than epsilon. Now all we got to do is show that it's bigger than negative epsilon. And to show that, well, that's why we define delta, so that delta is less than or equal to delta naught. With delta less than or equal to delta naught, we have 0 is less than absolute value of x minus 0 is less than delta is less than or equal to delta naught. And so we have absolute value of x minus 0 is less than delta naught. So now we can use the fact that this statement is true. This statement works for every real number that satisfies this property. Well, x satisfies this property, so it must work for x. So we can conclude that this inequality is true. So absolute value of cosine x minus 1 is less than epsilon, but that means that cosine x minus 1 lies between negative epsilon and positive epsilon. And because of this, we have that negative epsilon is less than cosine of x minus 1, which is less than all of these guys. And so this is what we're able to arrive at. We have that sine x over x minus 1 lies between negative epsilon and positive epsilon, which is exactly what we wanted to show. And because we have sine x over x minus 1 between negative epsilon and positive epsilon. This means we have absolute value sine x minus 1 is less than epsilon, which is exactly what we wanted. So we have proven this statement, which means we have proven this limit. And so this completes the proof. And so yeah, that's pretty much it for this video.